The year 1961 witnessed a confluence of intellectual currents, a period ripe for groundbreaking discoveries. In this environment, John Horton Conway, a mathematician of extraordinary talent and a knack for elegant simplicity, began to lay the groundwork for what would become a seminal contribution to the field of game theory and, more broadly, to the very fabric of mathematics. The work, though initially embryonic, would blossom into a profound exploration of numbers and games, fundamentally altering how mathematicians perceived. The intellectual genesis of Conway's pursuits stemmed from a dissatisfaction with the prevailing definitions of numbers and their limitations when applied to games. Traditional number systems, while robust within their established boundaries, failed to adequately capture the strategic nuances inherent in combinatorial games. Prior to Conway's work, the theory of games existed, of course, but lacked the unifying conceptual architecture that would allow for a comprehensive analysis of a vast spectrum of games. The groundwork had been laid, notably by the work of Sprague and Grundy on impartial games, which had provided tools for analysing games like NIM. However, a truly general theory encompassing both impartial and partisan games, those where players have differing options, remained elusive. This pre-existing landscape, a terrain of fragmented insights and unanswered questions, set the stage for Conway's revolutionary approach. He sought a new way to construct numbers, a system that would not only accommodate the familiar real numbers but also encompass a broader class of entities capable of representing the outcomes and relationships within combinatorial games. The key insight involved defining a number strictly in terms of the sets of numbers it could possibly be greater than or less than. This seemingly simple definition, expressed recursively, proved to be extraordinarily powerful. The core tenet of Conway's system lies in the remarkable construction of numbers. A number, in this context, is defined by two sets. The left and right sets contain other numbers. A number is considered the simplest number, that is greater than all numbers in the left set and less than all numbers in the right set. This definition, while deceptively simple, allows for the construction of an entire universe of numbers. Beginning with an empty left and right set, we get 0, then, placing 0 in either the left or right set, we get numbers like 1 and -1. With these numbers in place, we can construct fractions like 1/2 and 3/4. The process continues indefinitely, generating numbers that include the familiar real numbers, along with infinitesimals, numbers that are infinitely close to 0 yet not equal to 0. It also allows for the construction of numbers that capture the complexities of games. Conway's work introduced the concept of surreal numbers. These surreal numbers serve as a foundational concept of his system. It is the most general construction of numbers possible. While the real numbers and their extensions form a well-defined and important subset of the surreal numbers, the full scope of the surreal numbers includes infinite and infinitesimal quantities. They provide a unified framework for understanding both continuous and discrete mathematical structures. The practical implications were immediate and far-reaching. Conway's framework provided the first robust method for assigning a numerical value to the outcome of a combinatorial game. These values, which can be thought of as the worth of a given position, could then be utilized to analyze complex game positions. Conway further demonstrated how these values could be combined and manipulated in predictable ways, enabling a systematic approach to game analysis. He was able to provide a framework for understanding the structure of games, identifying winning strategies, and classifying game positions. Conway's system allowed mathematicians to rigorously compare and combine game positions, revealing surprising relationships and opening new lines of inquiry. The immediate impact of Conway's work was felt within the relatively niche field of recreational mathematics. It allowed for a systematic study of games such as Go, chess, and, notably, the game of NIM. However, its influence eventually extended into other domains. The underlying mathematical structure illuminated the intricate connections between games and numbers. This gave rise to numerous applications in theoretical computer science, economics, and even physics. The early reception of Conway's ideas was enthusiastic among mathematicians and game theorists. The elegance of his constructions and the revolutionary nature of his insights quickly captured the attention of leading figures in the field. The resulting academic paper or book, which expanded upon these initial ideas, solidified Conway's position as a leading figure in modern mathematics. Critiques, as they did emerge, were primarily focused on the esoteric nature of the surreal numbers. Some found the concept of manipulating infinitesimals and infinite numbers challenging. However, the core of Conway's methodology provided a workable and valuable tool for the study of games. The work's lasting legacy stems from its profound impact on the fields of game theory and mathematical logic. Conway's approach demonstrated the power of abstraction in mathematics. The surreal numbers, an example of a number system far exceeding the traditional reals, showcased the potential for creative mathematical construction. Other mathematicians and scientists have utilized Conway's work to interpret models of complex systems, demonstrating the power of game-theoretic models. Conway's work was directly influenced by the prior work of mathematicians and other researchers in the field of game theory, namely those who investigated combinatorial games. This includes the work of Sprague and Grundy. Their work had laid a foundation for understanding the mathematical structure of games, particularly impartial games, where players have the same set of moves available at any given time. Conway built upon their foundations. He worked toward the creation of a more general framework for the analysis of a wider range of games. Conway's creative vision also benefited from the insights of other mathematicians. His use of recursive definitions, commonplace in modern mathematics and computer science, was an innovative approach when applied to number construction. The work of Cantor on transfinite numbers demonstrated the power of extending the concept of number beyond the familiar. Conway's work can also be considered an extension of this tradition. The influence of Conway's work can be seen in many subsequent developments. The theory of impartial games, built on the foundation laid by Sprague and Grundy, was significantly expanded by Conway's approach. He provided the tools to analyze game positions. The development of combinatorial game theory, as a distinct discipline, is a direct result of Conway's contributions. It has found applications beyond recreational mathematics. Economists use it to model strategic interactions, and computer scientists use it for analyzing algorithms. Conway's exploration of numbers and games has inspired generations of mathematicians and computer scientists. His work has contributed to how we understand decision-making. This in turn influenced the study of artificial intelligence and its ability to create intelligent algorithms. The simplicity of his concepts has led to a richness of results. In conclusion, the work of John Horton Conway, beginning in 1961, represents a pivotal moment in the evolution of mathematics and game theory. His ingenious construction of numbers laid the foundation for a revolutionary framework for analyzing games and, by extension, a profound broadening of our understanding of mathematical possibility. His legacy is one of brilliance, creativity, and enduring influence across various fields. The surreal numbers have become a cornerstone of modern game theory. Conway's work continues to inspire new research and new innovations.